We have earlier said that the atom is the smallest unit of matter where we have a pure substance. It is the smallest identifiable unit of an element. Elements cannot be broken down further by chemical means. All the known elements are organized in the periodic table. 91 or so are found in nature in varying amounts, and about another 24 have been made synthetically. The ancient Greeks were the first civilization to look closely at the world around them and tried to find explanations for what they saw that were rational and based on a god or gods. They were the first to try and explain matter. There were two schools of thought. One thought that matter would be continuous, that when it was broken down enough that it would have the properties of mathematical points. The other school argued that when broken down enough, the particles would still have a finite size. Of course, neither side backed their arguments with experimental data. Even though some early scientists believed in matter being made of atoms, there was no scientific evidence for the argument until about 1800. John Dalton based his atomic theory on two recently discovered laws. The first was Antoine Lavoisier's law of conservation of matter, that matter can neither be created nor destroyed. The second was Joseph Proust's law of definite proportions, that compounds were made up of elements and that the elements were always in the same proportion by mass. In other words, that if one decomposed water, one would find that it was always 89% oxygen and 11% hydrogen by mass. The major points of Dalton's theory are as follows. 1. Each element is composed of tiny indestructible particles called atoms. 2. All atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. 3. Atoms combine in simple, whole number ratios to form compounds. Dalton's points are all consistent with the two laws listed on the previous slide. He also assumed that the atom was spherical and homogeneous. In the 19th century, problems with Dalton's atom arose. Charged particles were found. Their existence in matter was at odds with what Dalton had proposed. Still, his theory held sway for about 100 years. It wasn't until 1897 that J.J. Thomson and his group characterized what is now known as the electron. It was then called the cathode ray. The cathode ray was very small, negatively charged, and found in all types of matter. Thomson didn't know how small, but figured out what is called the charge-to-mass ratio. Because this didn't fit with Dalton's theory, he modified it. Thomson's model is called the plum pudding model. Since matter must overall be neutral, the negative electrons were embedded in a positively charged sphere. Thomson's model didn't hold for very long. Ernest Rutherford and his group performed a classic experiment that ended up showing that the atom had an exceptionally dense, positively charged nucleus and otherwise consisted mostly of empty space. As the figure shows, there is a source of alpha particles, recently discovered radioactive particles about 7,000 times the size of an electron, positive charge 4 times of the electrons. The setup had a detector surrounding an exceptionally thin piece of gold foil. Alpha particles were only allowed in through a slit and had to go through the gold foil. If J.J. Thomson's model had been correct, the alpha particles would have all gone straight through the gold foil and landed in the same place on the detector. However, almost all the alpha particles behaved as expected. There were very few that were deflected at various angles. The angles varied from very slight to extremely large. Some of the alpha particles were deflected almost straight back. Since this was at odds with the existing theory, Rutherford had to propose a new one. Rutherford's experiment was consistent with an atom that had a very dense positively charged nucleus. Positive alpha particles were deflected after all. Electrons were posed to be in the empty space outside the nuclei of the atoms. If one were to imagine the nucleus being the size of a marble with a diameter of a nickel, the edge of the atom would be about 1/2 mile away in every direction. We will pick up on atomic theory in a later chapter.